Hello everyone, welcome to the next session of Strength of Materials. In this session, I am going to talk about a topic, stress and strain in composite bars rigidly connected in parallel. You can see there are two bars, 1 and 2. They are rigidly connected, which means one side is fixed and on the other end I have a load P applied on both of them. Let P1 be the load acting on the first bar. L1 is the length of this bar, A1 is the cross-section area, E1 is the Young's modulus of the first bar, and these are the corresponding values of the second bar. When you have two bars which are rigidly connected and they are in parallel, it is said that this load P is actually shared by both the bars. So P is P1 plus P2. This is one equation which needs to be noted. When I talk about load, I can also talk about stress. Say in the first bar the stress is sigma 1. Sigma 1 will be P1 by A1, and for the second bar stress sigma 2 will be P2 by A2. Here I can say therefore P1 will be sigma 1 A1, and here I can say P2 will be sigma 2 A2. This is something which we have already discussed. So when I substitute these terms in equation 1, I get therefore P is equal to sigma 1 A1 plus sigma 2 A2. This equation is useful in case the total load coming on the body is known. I also know the cross-section areas and I have to calculate the stress. Or suppose if I know the stress and the area and I have to calculate the total load coming on the body. So this kind of equation is very useful. I mark this as equation number 2. This equation also needs to be remembered for solving numericals. Next, we will talk about another equation which is applicable in this case. That is the strain in bar 1 will be equal to the strain in bar 2. This is obvious. Otherwise, suppose if you see a structure like this and the next day you will observe that this load has caused the bar to bend like this. I mean to say the first bar is still straight and the second one has got tilted, which we do not observe. For example, if you see your reinforced concrete structures around you, the columns, they are consisting of concrete block and there is steel bars inside to give it more strength. You never see that the concrete block is bent like this or like this. It is always straight, which means the load acting on this block will be shared by these bars and by the concrete, which is also called as a matrix. So this is an example of a composite bar. So strain is equal for both. So therefore I can write down strain is E1 is equal to E2. This is the main equation. Strain is sigma upon capital E by Hooke's law. Therefore I can write down sigma 1 upon E1 is equal to sigma 2 upon E2. So this is also another equation that we can use. So equation 1, 2 and 3 needs to be remembered and recollected while solving numericals. Now we'll go to another topic which is called as modular ratio. It is the ratio of moduli of two different materials. By the term moduli, I mean Young's modulus. So here you can see it is represented by small m and it is the ratio of E1 and E2. These are the two material in the say concrete structure. Say I can say this is my RCC column and there are some steel bars inside. There can be n number of steel bars. So here there will be E of steel and there will be E of concrete, both. So you will also have to observe that this value of M is always greater than 1. Since it is greater, therefore it will always be the ratio of higher to the lower value. E of steel will be more as compared to concrete. So I will write E of steel upon E of concrete. So this is about the concept of modular ratio. Suppose if I know the value of modular ratio also, if it is given as 2.4 and I know E of steel is 2 into 10 raised to 5 Newton per mm square. So there is a particular mixture of concrete. It is very simple for me to find this value because I know this ratio. And I also know that E of steel will always be greater as compared to E of concrete because steel is more elastic as compared to concrete and concrete is more brittle. So these are the two concepts which we need to know. Based on this, I'll be solving two numericals now. Let's take up the first one. A load of 270 kilonewton is acting on a short RCC column of size 200 mm by 200 mm. So suppose if you have a column like this, the size is going to be 200 by 200. So I'll write down the data. The load P is 270 into 10 raised to 3 Newton. The size means the area of concrete is 200 by 200, which is 40,000 mm square. The column is reinforced with 10 bars of 12 mm diameter, which means there will be, say, 10 bars. So there is a 10th bar somewhere. I'm just drawing a random diagram, and the diameter of each bar is going to be 12 mm. So I have diameter of this steel is going to be 12 mm and number of bars is going to be 10. Determine the stresses in steel and concrete if the modulus of elasticity of steel, E of steel, is 16.5 times that of concrete. I need to find the stress in steel and in concrete. So sigma S and sigma C is what I need to find. So the question is very simple. I will first calculate the area of these steel bars. If I have to calculate the area of steel bar, so area of steel bars will be pi by 4 d square. Correct? So this is just the cross section area and this has to be multiplied with n. So this will be pi by 4 into 12 square into 10. This will be 1131 mm square. Okay, so this is the area of the column given to me totally. If I want to calculate the area of concrete, that will be area of column minus area of steel. Let me call it as AS. So this will be AC minus AS, which will be 40,000 minus 1131, which will be 38869 mm square. So this is the value of area of concrete, which is here. So now I'll start using my equations. The first equation that I'll be using is the total load, P value is known to me, is sigma of steel, A of steel, plus sigma concrete, A of concrete. It was sigma 1, A1. So here 1 is steel, 2 is concrete. So this value is known to me, 270 into 10 raised to 3 is equal to, I do not know the value of sigma S. I know A of steel is 1131 plus sigma C is not known to me. I know the area of concrete 69. So this is one equation that I get. I'll mark this as equation 1. The second equation which I'll be using is strain is equal. So I can say that strain in steel will be strain in concrete. So here I can write down sigma S upon ES is equal to sigma C upon EC. I know the relation of ES and EC. So I can write down sigma S is equal to ES upon EC into sigma C. Here I already know the equation. So I can write down therefore ES upon EC is equal to 16.5. So I'll be substituting here and I get 16.5 times sigma C. So I get the relation for sigma S and sigma C. When I substitute equation 2 in 1, I'll get the value of sigma S as 77.385 Newton per mm square and sigma C is 4.69 Newton per mm square. So these are the two values that I obtained. Let's take up another numerical. A square RCC column is 300 mm by 300 mm in cross section. Similar to the previous problem, again the size of this column is 300 by 300. In mm. It is reinforced with 4 bars of 20 mm diameter. So now there are 4. I'll just jot down the data. I'll write down area of column is 300 by 300, which is 90,000 mm square, and I have N as 4 bars. I have its diameter as 20 mm. Determine the load carrying capacity of the column, which means I need to find the value of P. If allowable stresses in concrete and steel, this is very interesting because sigma of concrete and sigma of steel is known to me. So it is 7 MPa, which is 7 Newton per mm square, and 140 MPa, which is 140 Newton per mm square. E of steel is given as 200 gigapascal, which is 2 into 10 raised to 5 Newton per mm square. I am not showing the conversion because I have shown it many times in my lectures previously. And modular ratio, this is interesting, is given as 13. I have to find the value of total load exerted on this column P. So I'll start solving on the similar lines. I know the area of column. I want to find the area of steel. Say I call it as AS, will be N into pi by 4 d square, which will be 4 into pi by 4 20 square. So the answer is 1256.64 mm square. If I want to calculate the area of concrete now, because steel and concrete both are going to resist the load exerted on it. So area of concrete will be area of column minus area of steel, which will be 88743.36 mm square. This is what I get as a answer. Again, I'm going to use the same formula which I've used in the previous problem. Total load is equal to sigma S AS plus sigma C AC. I don't know the value of P. Now here the interesting part is sigma S and sigma C is known to me, but I will wait and I will write down E of steel is equal to E of concrete. Here if you see, it will be sigma S upon ES is equal to sigma C upon EC. So sigma S is equal to ES upon EC into sigma C. ES upon EC, which is a modular ratio, is given to me as 13 into sigma C. So I mark this as equation 1. Now if you observe, there is a relation between sigma S and sigma C, which means that I directly cannot take sigma S as 140 and sigma C as 7 megapascal. I will have to also satisfy this equation over here. Now for that reason, let us start with assuming sigma S is equal to 140. When I assume sigma S as 140 and I substitute here, I will get the value of sigma C as 10.76. Now if you look here, the maximum value possible for concrete is 7 megapascal, which means I cannot take the value of sigma S as 140. Now we will just reverse the case and I'll substitute sigma C as 7 megapascal. If I assume as 7 megapascal and I substitute here, I will get the value of sigma S as 91. I get the answer of sigma S as 91 megapascal, which is actually less than 140 megapascal, which means I can assume that this combination is correct for my numerical. I cannot assume this combination because it should be less than 7 and not more than 7. That is the permissible value given to me in the question. So I will be choosing the value of sigma C as 7 megapascal, and therefore from here I get sigma S as 91 megapascal, which is less than 140 megapascal. Therefore, or hence it is safe, and I am going to assume this combination, which has to be noted. Now when I go back to this equation, here sigma S and the area value of steel is 1256.64 plus sigma C, let it be the way it is, and area is 88743.36. I mark this as equation number 2. Okay, so now you can substitute these two values in this equation and you will get the value of P. When I substitute these values here, I get the value of P as 735.55 kilonewton. Technically you should have used this equation first and then this equation. So I just didn't want to change the pattern, so I left it the way it was. But you just have to understand that in this numerical, you will have to start from here. Had I started from here, you would have said that I know how to solve. Yes, I definitely know it, but this is a proper way of solving. So here, rather than writing 1 and writing 2, you can write this as 2 and 1 or A, B, something like that, in case you don't want to write 2 before 1. So accordingly you can solve, and this is just a rough calculation that I have shown you. So with these numericals and the theory which I have shared with you, I'm going to end this lecture. In the next session, we will discuss about a very important concept of stresses and strain, which is temperature, stresses and strain in a particular object. So I hope you have understood this lecture. If you have any doubts, write to me in the comment section. Don't forget to like, share and subscribe to my channel. Hit the bell icon for latest updates of my videos. I'll see you in the next session. Thank you.